Hi, I'm Justin with Mixel, and today I'll be presenting MIPI CSI-2 in low-power image sensors for industrial and consumer IoT applications, co-authored with Brian Lankowski of AMS OSRAM. So I'd like to spend a little bit of time to introduce Mixel. So Mixel was founded in 1998, and we've been a leading provider of mixed signal IP with an emphasis on the PHY. Those would include your MIPI PHYs, the D-PHY, C-PHY, and M-PHY. We also have an LVDS SerDes, and a few multi-standard SerDes, including a C-PHY D-PHY combo IP and an LVDS D-PHY combo IP. We've been a contributing member of the MIPI Alliance since 2006, and we were the first IP provider to demonstrate silicon-proven D-PHY, C-PHY, and M-PHY. We offer a complete integrated solution, including the PHY, controller, and FPGA platform, and we offer the widest support of optimized PHY configurations, including some patented topologies. And we have the widest coverage in terms of process nodes and foundries in the industry for MIPI PHY. We're silicon proven in 12 different nodes and at 8 different foundries. So let's spend some time today to talk about where low power image sensors are used in IoT applications. So there are some common requirements for these types of sensors. Many of them require additional sensitivity in both visual and near infrared spectrum. They are often power sensitive, require low power consumption. Many of them are battery operated, and they also require low and small form factor. There's some design integration challenges for these small sensors. They often use global shutter to eliminate motion artifacts. So these kinds of applications include AR, VR, and other wearables for head tracking, face tracking, and eye tracking. They're used in robotics and drones for simultaneous location and mapping navigation solutions, or SLAM. They're often used in mobile, consumer, and computing applications for biometric access control, head tracking, and face tracking. And they're used in industrial and home and building automation for presence detection, smart door detection, flow control, pick and place, object detection, and barcode reading in logistics. So with that, let's talk a little bit more about the Mira 050 that comes from AMS OSRAM. So this is a high-speed global shutter CMOS image sensor in the visual and near-infrared consumer applications. It is a stacked sensor made up of 2 chips with an optimized silicon layer for pixels and a readout layer. And the Mira 050 uses the MIPI protocol to communicate at the highest frame rates of up to 290 frames per second, allowing for fast interception with a compact form factor and dedicated low power modes. With the global shutter backside illuminated design, the sensor has a quantum efficiency of 93% and a dark current of 30 unit electrons per pixel per second at 60 C. So one of the biggest design considerations from the Mira 050 versus previous generations of sensors from AMS OSRAM was the change from LVDS to the MIPI interface. This allowed for a smaller footprint, as MIPI allows for compact integration into the sensor packaging, lower power consumption, and better performance. And the ultra low power consumption with on-chip power management, which adapts to exposure, frame rate, and region of interest with MIPI. So in terms of footprint, the footprint efficiency is up to 3 times smaller, with higher sensitivity, lower power consumption without compromising on overall performance. So let's take a specific use case. In this case, let's look at e-door locks. So we can use 2 sensors from AMS OSRAM, the Mira 050 and the Mira 220. Both of these are in the Mira product family, and both of these sensors use Mixel's MIPI IP. Now with the Mira 220 image sensor, we can use the 940 nanometer dot projector. With the Mira 050, we can use the 940 nanometer flood illuminator. Now, for biometric access control, you need to have a reliable and accurate face authentication. So a 2D image is not sufficient. So we can combine images from both of these sensors, stereo vision camera with the IR flood illuminator, and the single camera with dot projector to get the depth information for accurate and reliable face recognition. Here on the right, you can see some requirements for this sensor subsystem. Many of these relate to the requirements we were talking about earlier. And one additional feature of this sensor that's required for this application is event detection for automatic system bring up. So let's look a little bit more closely at this specific feature from AMS OSRAM's Mira 050 image sensor. So the sensor remains on in a low power state until an event is detected. So in context A, it's in a low frame rate, the image is subsampled at 1 to 8, and event detection is enabled. And when a tile gets flagged, it'll switch to high frame rate, still keeping on full region of interest, but no subsampling, and event detection is turned off. So what this means is, in a lack of movement, the sensor stays on in low power mode where the minimum required data is transmitted using the MIPI interface. And when an event is detected, the sensor switches to a higher frame rate. This allows the sensor to stream with programmable resolution, consuming only 3 milliwatt in programmable resolution when compared to 75 milliwatt. So how is MIPI used in the mirror image sensor? The image data and metadata are transmitted off-chip using the MIPI CSI-2 version 1.3 and MIPI D-PHY version 2.1 interfaces. The CSI-2 protocol layer handles the packetization, and the MIPI D-PHY physical layer handles the low-power data transport. Now, MIPI CSI-2 is the preferred interface because it allows for data transport in RAW 8, RAW 10, and RAW 12 packets, and the metadata to be transported as embedded 8-bit non-image data. The MIPI D-PHY allows for high-speed data transfer while going to low-power states in between data bursts. This is achieved using the specialized ULPS, or ultra-low-power state, which allows for low-power modes on the sensor, and fast cycling between ULPS and streaming modes. So why is MIPI often used in IoT sensors, cameras, and ISPs? MIPI was designed from the ground up to minimize power requirements while supporting high bandwidth and strict EMI requirements. And many IoT sensors are battery operated, so they are power sensitive. MIPI CSI-2 is widely adopted today in the ecosystem for sensor applications. So if you're developing a new sensor or a new ISP, you would use MIPI CSI-2 to tap into the established ecosystem. And MIPI D-PHY was the first MIPI PHY and is still widely adopted today. So Mixel provided AMS OSRAM with our D-PHY CSI-2 TX Plus IP. This IP supports one lane at 1.5 gigabits per second per lane in high-speed mode and 10 megabits per second in low-power mode. It supports MIPI D-PHY version 2.1 as a specification and MIPI CSI version 1.3 of the specification. And TX Plus is a Mixel proprietary implementation that allows for full-speed loopback and internal testability without the area penalty of a traditional universal configuration. And as always, we achieve first-time silicon success. So with that, I'd like to leave you with a couple of closing thoughts. Low-power sensors are used in many different industrial and consumer applications today, and MIPI specifications were designed from the ground up to reduce power and reduce area, and they're widely implemented in these sorts of applications. And AMS OSRAM was able to leverage specific features of Mixel's MIPI D-PHY and the CSI-2 IPs to improve the overall power and efficiency of their Mira product family. Thank you for listening today.